Here we are with exercise 14. This is the last exercise in this series on SVD for image denoising, the last exercise in this chapter, and the last exercise in this book. So if you made it this far, that is absolutely amazing. I'm proud of you. Your grandmother is proud of you. You should be proud of yourself. Okay, let's get down to business. Now, we saw in the previous exercise that it seems like the first components 2 and 3, which are indices 1 and 2, contained all of the noise, or at least most of the noise. So the idea here of this exercise is to try to project out that noise. Now, the way we do this is mechanically, mathematically, it's exactly the same as the low rank approximations. The only difference is which components we are projecting out. With the low rank approximation, we reject out the lowest, like the sort of meaningless components that have the smallest eigenvalues or the smallest singular values. Here, we actually want to project out whichever components we think are dominated by or purely defined by noise. Now, in this case, that's these two components, component number 1 and component number 2. So the second and the third component. And then, basically you want to reconstruct the entire image using all of the other dimensions, all the other layers in this image. And it looks pretty good, when we compare the original noisy image to the projected out image. We certainly get rid of a lot of the sine wave component here, so you don't really see the sine wave, but you also see that it's not perfect, doesn't perfectly get us back to the original image that we imported several exercises ago before adding any noise to this. So yeah, it's pretty good. It's not perfect. And yeah, we could go through and look for lots of other individual components to project out. And if you'd like to do that, then obviously I always encourage exploration using the code. But to be honest, I think if I saw a result like this and I were trying to project out this image, I would say there's probably better ways. We might want to do some kind of multivariable regression modeling to regress this sine wave or model this sine wave and project it out using modeling. That is a topic for another discussion. That would be something you would study in, computational vision and image processing and so on. Nonetheless, here we are focusing on the linear algebra aspects of this exercise. I hope it's clear what to do. And now I'll switch to Python and show you my solution. So here I define a NumPy array with the components that I want to project out. So component index 1 and index 2. So then we actually want 2 images. We want just the noise image. And this is just for visualization. We don't actually use this in the computation. So here, this is again the multiplication of U times sigma times V transpose. But then here I'm only selecting the noise components. So pretty straightforward. Reconstructing the image with the noise projected out. There's a little bit more code here, but that's because the way I decided to implement this was by creating a vector of Booleans. So a Boolean vector where all of the elements are set to true, and then the noise components I set to false. So basically, this is going to be a vector of all trues, and the first or the second and the third element is going to be false. And then I use that here. So this is just the coding mechanism that I use to reconstruct the image without those 2 components. All right, so here we can see what the results are. So again, as you saw in the book code, I think this actually looks really neat. I'm calling this noisy, but it looks really cool to me. But, so let's see, here's the first 2 components. Yeah, and like you saw in the book figure, this looks pretty good, but not perfect. But, I think you understand the concept of using the singular value decomposition to isolate some noise and try to project it out. Although it didn't work perfectly in this case, with this particular example, this is a pretty common method in data science and modern statistics to identify and remove noise from a data set. Okay, so here, I'm just trying to give you some inspiration for ways to continue exploring this technique using this code. So you can make a histogram of the noisy image, and we can make a histogram without this. So you can see This has these two sharp peaks here. It's very typical for a distribution of a sine wave. So sine waves have a distribution that looks like this, almost looks like an inverse Gaussian. Actually, now looks like a smile, right? We need some eyes over here. But yeah, we can see for contrast, here you see most of the images, most of the image pixel values are 0 or 1 with just a couple of grayscale images in between. Anyway, I hope you enjoyed working through this exercise and feel like you really have a better understanding of the singular value decomposition and how to use it in various applications.